Hello, everybody, and welcome to another wonderful day of chemistry. So today we're going to be taking a slight break from talking about separate molecular species to talk about big solid molecules, and things are going to get a little charged as we talk about salts. So one of the first things to keep in mind, we've already seen this a little bit, not all elements form separate molecular species. A lot of times what we end up forming is solids. So these are going to often form by interactions of various elements to generate a whole macroscopic object without any of the individual separable molecules. One of the most common ways you can do this is by making a solid through ionic or charged interactions. So what we do in this case is what we have is an equal number of cationic and anionic charges, which essentially are going to want to coordinate to make an overall neutral species. Because turns out having an overall charge is very unfavorable, but positive likes negative. So everybody's going to try and get together. So what we end up having is, say, a mixture of positive cations like sodium and negative anions like chloride. And so what will happen is every sodium is separated from each other by negative charges, because while positive doesn't like positive, they both like negative. So I can hang out with you as long as the main objective is I'm hanging out with him. And this is the general way that these ionic compounds work. And overall, we should have a net neutral charge. And this forms a lot of very common objects, such as good old table salt, which is just a mix of sodium and chloride. So because all of these ionic compounds are pretty much infinitely large, there's going to be moles worth of sodium and moles worth of chloride. We do need a shorthand way of talking about how many ions are present. So the preferred notation is essentially called the formula unit. So this is pretty much an empirical formula for an ionic compound. Same basic idea, it's going to be the smallest whole number ratio. And so, for example, if I'm looking at sodium chloride, the formula unit is sodium chloride. They're present in a 1-to-1 ratio. So I can't get any smaller. And if I did, I'd have fractional units. So this should always be a fairly simple formula. And most importantly, we should have an overall neutral charge. I've got a +1 charge on sodium. I've got a -1 charge on chloride. The positive and the negative cancel out. However, what this often means is that in order to determine a lot of our formula units for other species, we're going to want to know the charges of each individual element ion in order to make sure that they cancel out. So for this, we can go to the periodic table to find some common charges. So we've seen some of this before. For example, alkali metals tend to form +1 cations. Alkali earth tend to form +2. Halides form -1. Oxygen and its cohorts form -2, then -3, then -4, as we're working from the right side. Metals are a little bit more messy, and we'll be talking about them a little bit more next time, except for a couple nice simpler species such as aluminum, which forms +3, and things like nickel and cobalt and manganese, which also always form a +2 charged cation. So what we can do is use these charges to determine the structure of a simple binary ion. So binary ions are defined by having one type of cation and one type of anion. And these are actually fairly easy to describe, as the total charge has to be 0. So we can use the ratio of charges to find the ratio of individual cations to anions. So if both of my ions have the same magnitude of charge, then they'll always form a 1-to-1 complex. So this is true for sodium chloride, +1, -1, but it's also true of calcium oxide, +2, -2. If the charges are numerically different, then a good place to start is use the charge for the cation as the subscript for the anion and vice versa. So we can see this for aluminum oxide. So this is going to be, well, pretty much that sheen that you get on aluminum. It's a very common uh, ionic compound. So aluminum has a plus 3 charge. Oxygen has a minus 2. So if I've got 2 aluminums, I'll have a positive 6 charge. And if I've got 3 oxygens, I have a negative 6. And by switching the charges for the subscript of the other species, I guaranteed that the charge of aluminum is canceled by the charge of oxygen. We can also do this for calcium phosphate, which follows the same general trend. Calcium has a plus 2 charge, phosphate has a minus 3. So I have 3 calciums, plus 6, and 2 phosphates, minus 6. Generates an overall neutral charge, which makes it a very kind of convenient method. When you're done making your molecular formulas, always double check to make sure that the charges cancel out. Also, occasionally you'll end up with a good ratio, but it might not be the smallest one. So it is also worth double checking to see if you can divide the numbers by a common number. So is it possible to divide both sides by 2 to get a whole number? In both of these cases, not possible. If you take something like calcium oxide, plus 2 minus 2, well, the formula isn't Ca2O2, it's CaO. We divided both sides by 2 to make sure we have that formula unit, or the smallest ratio. So it's a quick double check worth performing. You don't need to most of the time. However, now that I have these binary ions, we need to find a good naming convention. So binaries aren't too bad, but there can be a bit of memorization. The first part's fairly easy. You're just going to name the cationic species. So sodium plus is just sodium. Calcium is calcium. Aluminum is aluminum. It gets a little bit messy with the metals, but we'll talk about that next time. However, the anionic species are a little trickier. So if I have a Cl minus, I've got chlorine. However, we replace the ending suffix of chlorine with "ide." So anytime you see "ide," it's a way to say that I've got the anionic form. So chlorine becomes chloride, oxygen becomes oxide, nitrogen becomes nitride. Fluorine becomes fluoride, chlorine becomes chloride, bromine becomes bromide. So look for that ending suffix and change it to an "ide." All of these cases are fairly straightforward, as there's only one possible charge for all of these anions. Then these two names can be combined, and here's the beautiful part for all of these species. You don't need to include any information about the elemental ratio. The reason why is, as long as you know what charge the ions form, you should be able to back calculate the ratio of the two species. So for example, we have things like calcium oxide. This is more commonly known as quicklime, and it's very useful in making concrete. We also have aluminum chloride, which is used in a lot of chemical processes and sometimes to remove water from systems as a dehydrating agent. And you'll notice that it's still aluminum chloride, even though I've got 3 chlorines. The reason why is I know that aluminum always makes a +3 charge. Chlorine always makes a -1 charge. So I have to have 3 chlorines to cancel out that charge. So thus, it's really important to be able to figure out how to balance these compounds, because all you're usually given is the species present. However, next time we're going to be talking about a little bit more complex systems, as a lot of our anions are going to become polyatomic, and we're going to deal with some trickier metals. Until then, take care.